Now, this is the slide to make sure you understand, because what we have on the right is what's known as the Wigger's diagram. It shows you the interaction between the pressure in your aorta, the ventricle, the atria, the volume of blood in the ventricle, the electrocardiogram, so the actual electrical conduction of the heart, and then the phonogram, so the actual sound the heart's valves are making as they open and close. So if we look down here, we can see if we look from left to right, that's going to be time. So we can see how we have our P wave, then we have the increase in ventricular volume. This is the atrial kick from the atria depolarizing and pumping. Then we have our ventricles depolarized, and now they're producing pressure until they overcome aortic pressure, and then blood's going to leave the heart. The ventricles repolarize, pressure comes back down, blood's no longer leaving the heart. Now the heart is completely relaxed. The heart fills passively until, once again, we have another P wave, and then we have a kick. Follow your way through it. Make sure you read and understand these. Rewatch, re-listen to this component, and make sure you understand how that's going to work. Now, when the heart is relaxing, that's when we're going to have that mitral valve open, and that's when the ventricle is going to be filling. Now, notice most of that ventricle filling is done passively. The last 30% of it is from the atrial component, from the atrial kick. Now, here's the thing. That's how you can live without atrial function. Now, that doesn't mean you're going to be an optimal athlete, but that means you're going to be at least alive. So that's why you can have atrial fib, atrial flutter, and you're going to make it. It's not optimal, but you're going to make it. Whereas if you want to have high-level athletic performance, you need to make sure everything's happening like it should. Now, the amount of blood the heart beats per beat is what's known as the stroke volume. So at the end of the diastole, so end diastolic volume, EDV, the heart is as full of blood as it's going to get. Then we have end systolic volume. There's always going to be some blood left over after the heart fully contracts. So if we have how much blood we had at the very end and how little we had left, the beginning minus the end gives us the total amount of blood we pumped in that beat. That is our stroke volume. Our ejection fraction is the percentage of blood that was pumped out. So we take that stroke volume and we divide it by the end diastolic volume. And this is going to be a good indicator of how healthy your heart is. A healthier heart is going to have a higher ejection fraction. Now, usually it's in the tune of 60-odd to 70-odd% at rest. Can be a little bit better at moderate intensities and getting up to higher intensities, but we're not going to have a super high level as compared, or we're going to have a super low level. If you get down to like 30, 40, 20, now we're talking about individuals that are going through heart failure. Now, when we multiply the number of beats we have per minute, heart rate, multiplied by the stroke volume, the amount of blood we're pumping per beat, we get what's known as cardiac output. That's going to be the letter Q. So a higher cardiac output is a greater amount of blood that's being pumped through the body per minute. That's in liters of blood per minute. The average person, it's about 5 liters of blood. It's pretty much all of your blood volume gets pumped around you per minute. Now, this is going to go and increase massively whenever we start talking about exercise. Now, we have our vascular system, which is going to go from our arteries, which are major vessels, into our arterioles, which are smaller, to capillaries, where we actually get that gas exchange. And then we're going to collect into venules, and then finally into veins. And veins are the capacitance vessels. Those are the ones that are going to hold most of our blood when we happen to be at rest. Now, blood pressure, systolic, is going to be the highest pressure when the heart is contracting. Diastolic is going to be the lowest pressure in the artery, and that's when the heart is relaxing. So overall, we develop what's known as the mean arterial pressure. Since the heart spends essentially 2/3 of the time relaxed and 1/3 of the time contracting, the mean arterial pressure is going to be 2/3 of the diastolic blood pressure plus 1/3 of the systolic blood pressure. Why do we care about all these things? Well, just like pipes in a building, the pressure goes too high, they can burst. That's not good if it happens to be in your brain or your heart. Well, much less anywhere in your body. And so the systolic is the peak pressure we're going to see. Diastolic is going to be the lowest pressure we're going to see, but the more important one is the mean and the diastolic, because that's where you're spending most of your time. So if you just constantly have higher pressure through the pipes, that's going to be pushing more stress on them, which then can lead to aneurysms and otherwise. Now, when it comes to sending the blood through our body, we're going to see the greatest oscillations in pressures in the ventricle. So we're going to go from 0 pressure to max pressure. Then once we get to our aorta and our large arteries, we're going to have that higher pressure because blood's going to go from high to low. So we still get that peak coming off the heart, but then we're not going to come down as low because we have that pressure so blood can't backflow. because there's going to be that pressure that's going to be slowly pushing it down and down and down until we hit our lowest blood pressures when we're getting to our large veins. We're talking our vena cava, superior and inferior. And this is just the basic way that your blood moves through your body, is moving through pressure gradients. Now, this is good because our different vessels are going to be able to deal with, especially the large arteries and arterioles. They have a lot of smooth muscles. They can vasodilate, vasoconstrict, but they can deal with those forces of the greater amount going. And the total amount of resistance to blood flow is going to equal essentially what is going to be the properties of the length of the vessel and otherwise, and the volume that we're pushing through it over the radius of it to the fourth power. So the bigger the radius, the lower resistance. The lower resistance, the easier it is going to be for blood to flow around that area. So blood flow is really just looking at our change in pressure divided by our resistance. Now, vasoconstriction is when we take those vessels and we shrink them down, and then vasodilation is when we're going to expand them. Now, this is great because it allows us to shunt blood where it needs to be, where it doesn't. So when we start exercising, we're going to see that vasoconstriction to things like our digestive system. But we're going to see vasodilation to our muscles. And obviously this is great because now we're sending more oxygen to those muscles, so they're going to be able to they're going to be able to do the work they need to, and we're not going to be diverting energy to the areas of the body that aren't as important at the time. So what we're going to find is the greatest amount of vasoconstriction and dilation occurs in our arterioles. And so this is going to be what's giving us those greatest changes in pressure because of that left ventricle going and pumping the blood through the body until we get all the way back to that right atria. So here's an example of the total amount of blood flow to the areas and how those are going to change accordingly from when we go from being at rest to high level exercise. So we're going to see that the brain is going to have a lower percentage of cardiac output, but it still gets the same amount of blood flow essentially. The heart, no matter what, whether it's working at max or minimal, is always going to get that same 4 to 5% of total cardiac output because it's what's pumping blood around, so it's always going to need good blood flow. Our digestive tract is going to get less blood flow, our muscles are going to get less blood flow, our kidneys are going to get less blood flow. Our skin is probably going to get more. It allows us to sweat and thermoregulate better. And then obviously our muscles are getting a massive increase in total amount of blood flow to that area. Now, we're going to make sure that we're sending things where they need to be. The faster metabolism is going in the area, the greater the blood flow. At rest, guys, notice that our brain is taking up 15% of our cardiac output. For a tissue that's relatively small, just a couple pounds compared to the rest of us, it is taking up over 1/10 of the total output. That's because your brain turns out is pretty metabolically active, or hopefully is, and we're going to need to be able to match it. Now, as we go and get into higher intensity exercise, that's where we're going to see the vast majority. So we're talking maybe all the way, well over 3/4 of your total exercise blood flow is just going to your working muscles. Now, how we're able to get this vasoconstriction and vasodilation is due to a number of different control mechanisms. So these are going to come down to metabolic factors, endothelial factors, and myogenic factors. So metabolic mechanisms are going to be causing vasodilation. So this is going to be buildup of metabolic byproducts, release of hydrogen, increased levels of lactate, decreased levels of oxygen, decreased pH, increased carbon dioxide, increased temperature. Endothelial mechanisms are going to be done by essentially signaling molecules. So this is going to be from prostaglandins, nitric oxide, which is NO, which is a major vasodilator, as we see bodybuilders sometimes supplementing with nitrates, nitrites, arginine, citrulline that are going to be able to increase this. And then we've got our myogenic mechanisms, which cause both vasoconstriction and vasodilation. And that's literally the contracting of the muscles. The contracting of muscles literally is going to cause or decrease the amount of blood flow to the area, but then when they relax, we're going to have that vasodilation. That's why obviously most sport involves cyclical movement, so you're going to be able to have that recovery. But any of you guys that have done really heavy weightlifting, you know that you have that effective vasoconstriction to those muscles when you're lifting, and that's why you literally are only going to be able to do so many reps of things like push-ups, pull-ups, because you can't get enough blood flow to the area to be able to maintain it aerobically. So what's going on for how we're controlling this? Well, it's going to also be affected by specifically our sympathetic nervous system. Epinephrine is going to be a global vasoconstrictor. Now, what's nice is we are going to get local vasodilatory effects, so that metabolic mechanisms, endothelial mechanisms, and myogenic are going to overcome the effects of epinephrine. However, at the same time, if we're always amped up and we're not doing anything, we're not getting those local factors. So now all we're doing is increasing our blood pressure, which is the reason why stress can kill you. Well, many other mechanisms adding on top of it, that's one of the kind of bigger linchpins. Now, the other side of it is when we have lower sympathetic activity, we're more relaxed, we're going to have a greater amount of vasodilation throughout the rest of the body. We're going to have better blood flow to all of our tissues. And we're going to find that most of the blood in our body at rest is really sitting in our veins. Now, once we start going in and exercising, that's where we're going to use also a bit of a myogenic pump, because there's little valves inside of our veins, so blood is only going to flow one way. And because of this, we're going to do a better job of returning blood to the heart, which in turn is going to give us a better cardiac output. Now, we're going to be maintaining this blood pressure by baroreceptors. They're effectively pressure receptors. These are good because we only want to have so much blood flow going to different areas of the body. If you put massive amounts of blood pressure going from your heart straight into your brain, you can potentially cause some negative issues. And that's why you'll have people that have issues with like seeing stars or blacking out after doing a heavy lift, because the blood pressure goes from being really high back to really low. And these baroreceptors have not been able to cause vasodilation again to those arteries and arterioles. And then someone might go a little nighty-night, or once again, they can have little visual disruptions because of those changes in blood flow to those tissues. Now, we also have chemoreceptors and mechanoreceptors. Now, the chemoreceptors are obviously detecting the chemical levels of different things like those metabolic byproducts, which in turn are going to go ahead and cause changes in pressure gradients. And mechanoreceptors are literally just detecting the stress. So the hard contracting muscles or otherwise are going to influence where our blood pressure is going to be. Now, this is a great example of talking about those venous return, which we're going to get by the muscles contracting. It's going to cause blood to go up. And then once it goes past the valve, it's not going to be able to have that valve reopen. Now, some folks can burst these valves, and that's where you kind of see like kind of squiggly veins on some bodybuilders and otherwise, where they've literally ruptured these valves from probably doing, you know, really intense exercise with relatively low, with really high pressures. Now, one thing else to keep in mind is a respiratory pump. So breathing in and breathing out is also putting pressure on the veins in your torso. And because of that, that's also helping return blood to the heart, which is going to allow it to pump a little bit faster. Now let's finally talk about the wonderful blood itself. Now, blood itself is there to obviously transport both nutrients, weights through to the body, to help us regulate that temperature, and to help us control our pH levels. Now, you're going to have about anywhere from 4 to 6 liters of blood. It's going to be even more if you're a much bigger human. And about 55% of that is plasma. So that's the fluid component. 90% of that is straight up water. 7% of that is plasma proteins like albumin, along with you're going to see things, the other percent is going to be things like your hormones. Then 45% of it is going to be formed elements, of which those formed elements are cells. 99% of that is red blood cells. Less than 1% of that is going to be your white blood cells and platelets, which help with you effectively getting your coagulation, so your clotting. Now, if we look at the ratio of formed elements to total blood, we have what's known as hematocrit. If our hematocrit is too low, it effectively means we got too low of an oxygen carrying capacity inside of our blood, and we're going to have issues with performance. On the other side, if our hematocrit is too high, our blood is too sludgy. Our heart has to work too hard to effectively pump this blood through our system, and because of that, we can actually risk things like myocardial infarction otherwise, just because we have this sludgier blood. There's literally been examples of athletes in the Tour de France that were utilizing drugs to enhance the red blood cell that died effectively of having too high of a hematocrit. So we're going to see that plasma level go down when we're dehydrated. We're going to see it go up when we're really well hydrated or really adapted to being out in the heat and otherwise. We're going to see those changes in red blood cells with training, where we're also going to increase the number a little bit, but we're not going to see that hematocrit really uptick. Now, that's going to be due to things like erythropoietin, which is going to signal for us to increase the red blood cell number, and that's done because we've had too low of an oxygen level, which you get from doing either really hard training, training at altitude, living in a hypobaric chamber, and or really being anemic, and then that's hopefully you get enough iron to go and replenish that. So What's interesting about our red blood cells is they don't have a nucleus, so they can't reproduce, they don't have mitochondria, so they can't use aerobic metabolism. So we have to constantly replace it, and that's done in our bone marrow. Each red blood cell is going to last about 90 odd days to 4 months, and we're going to be producing them the same way we're destroying them. Now, you literally get them a little bit fall apart every day just from the mechanical stress of being pushed through your bloodstream. Some of them are going to get destroyed because you bounce off something that you shouldn't have, aka think like a bruise. And then also, obviously, if you're female and you're menstruating, you're losing a certain amount of blood cells every single month. And so we need to replenish this. And that's why of all athletes, long distance female athletes have the highest risk of becoming anemic, simply because A, they've got the monthly phlebotomy schedule of menstruation, and then B, they get a lot of mechanical destruction of blood cells from literally their foot hitting the ground each step while they're going and doing running. So inside of red blood cells is hemoglobin, where that's the specific protein that's going to be able to carry oxygen to those cells and then go ahead and release it. And we're going to have obviously about as much of that as we can get, but we notice we need iron, you're going to need protein, and then you're also going to need a number of other vitamins and minerals to make sure you're keeping this up. So talked about the blood viscosity. If the viscosity happens to be too high, the heart is going to have to work harder just to go ahead and get that blood around our body. And that's the reason why we need to make sure that we are staying hydrated, because it also makes it literally easier for our cardiovascular system to work. And as we dehydrate, we have that thickening of the blood. The heart has to work harder, so it has to beat more because it cannot pump as much blood per beat. And that is going to give us what's known as cardiovascular drift, which we're going to get into much later on in the class. So thanks for listening. Go ahead and listen to anything and repeat it over and over again. If you guys have questions, please let me know. Otherwise, stay safe out there. Have a great day.